In this video, we're going to look at the reactions of amides. So amides are the least reactive of all of the carboxylic acid derivatives, and therefore you can't make acid chlorides from amides, you can't make anhydrides from amides, you can't make esters from amides. You can't really make anything other than carboxylic acids. And that's really the main reaction of amides in terms of making other carboxylic acid derivatives, is that they can be hydrolyzed. They can be hydrolyzed in either basic or acidic conditions, although acid hydrolysis is much easier. So we have a little bit of difference between that of esters and that of amides. Esters, we see that basic hydrolysis is a little bit easier. It's irreversible. We're also going to see that basic hydrolysis is irreversible with amides as well, but the reactions are very, very slow. And if we think about the reasons for this, again, we have to go back to the mechanism. Here we have now an amide, and so the leaving group in this case is NH2, and it's an extremely poor leaving group because it's so basic in nature. But it will react, amides will react with hydroxide. Again, basic conditions, we're talking about water, hydroxide. That's what you should always keep in mind. What reaction conditions are you in? In acidic conditions, you have water and hydronium ion, H3O+. In basic conditions, you have water and hydroxide. And again, water isn't a good enough nucleophile. It's not a strong enough acid to protonate the amide. But hydroxide is a good enough nucleophile to attack the carbonyl group, displacing that carbon-oxygen bond. So again, we're generating the tetrahedral intermediate minus, the Ti minus. But in this scenario, we have a situation where the NH2, like I said, is a poor leaving group. And so it takes a long time for the reformation of the carbonyl and the loss of that NH2. So that process is very slow and it generates a carboxylic acid. But notice, carboxylic acid plus the amide anion. And we know that amide is a very, very strong base, and so very rapidly that amide is going to deprotonate the carboxylic acid, and that is a very fast process to generate the carboxylate plus ammonia. And again, just like with esters, you're producing carboxylates plus the alcohol. With amides, you're producing carboxylates plus ammonia, or if or an amine if you had some R groups coming off of the nitrogen. So in order to generate a carboxylic acid, again, we have to acidify to get our carboxylic acid. And of course, in the process, we're going to also protonate the amine or ammonia, as it were, to get the ammonium salt. Now, let's look at acid hydrolysis. Acid hydrolysis, I said, is a little bit easier because this is also irreversible, and we're going to see why that is kind of at the end of the reaction mechanism. Again, in acidic conditions, we have water and we have the hydronium ion. The first step is always proton transfer to the carbonyl oxygen. Right? We generate our now Ti plus protonated carbonyl oxygen, and we have water, and that water can then act as a nucleophile and attack the carbonyl carbon. So we get addition of water to the carbonyl and displacement of that carbon-oxygen double bond. And we generate our tetrahedral intermediate, Ti plus, because there's a positive charge associated with it, where the water that we have added still has two hydrogens. So don't forget, common mistake is that students will just say, oh, there's an OH there. No, you're adding water to it. And so it has two protons. And those two protons don't automatically go away. They're still there. And we have to then deprotonate. We have to remove one of those protons, and we can use water to do so. So water removes a proton, and we generate our tetrahedral intermediate, our neutral tetrahedral intermediate. Notice we also regenerate our acid, the hydronium ion, in the process. And again, just like with esters, there are three spots that can get protonated by that acid, and if one of the OHs gets protonated, of course, we're going to go back to the amide. But if the nitrogen gets protonated, then we form, we have a positive charge now on the nitrogen. We have ammonia as a leaving group, which is a pretty good leaving group relative to that of NH2. And so we can kick off ammonia right away, stabilizing the intermediate with a pair of electrons from the oxygen, and we now regenerate our carbonyl that's protonated, and we have ammonia. So ammonia is a base, and so it can then remove that proton, and we form our carboxylic acid plus the ammonium salt. And now notice the ammonia is taken out of the equation because it is an ammonium salt. It is not a good nucleophile, and so it's not going to attack the carboxylic acid. And therefore, this reaction is irreversible as well. And that's why, generally speaking, when you're hydrolyzing amides, you're going to use acidic conditions. And of course it really depends on what you're trying to isolate. If you're trying to isolate the carboxylic acid, so the carboxylic acid would be neutral and generally less soluble in water as the acid, and you would work it up this way. If you wanted to isolate the amine portion of the amide, as it stands now, it's protonated, it's very soluble in water, so you have to then add base and neutralize all the acid and make it basic, make the solution basic, to get the amine instead of the ammonium salt. So let's take a look at a couple of examples here. Here I have N-methylbutanamide. And if I react N-methylbutanamide with water and sulfuric acid, again this aqueous acidic process, I generate my butanoic acid plus the methylammonium salt, right? So butanoic acid neutral plus methylammonium salt. And we've done a reaction just like this, where we took paranitro acetanilide. So here I'm showing you acetanilide reacting with sulfuric acid in water, and we hydrolyzed that amide bond. And so when you do that, you get the aniline salt plus acetic acid. And some of you may recall, when running this reaction, you smelled vinegar. It smelled like vinegar, and that's the acetic acid that was being liberated in the reaction. You may also remember that to isolate our product, we had to neutralize it with a base. And so we didn't want the aniline salt, we wanted the aniline itself, and therefore that would require us adding a base to neutralize the reaction conditions. Now, amides will also react with metal hydrides, and when metal hydrides react with amides, they actually produce amines. So if you think about esters reacting with lithium aluminum hydride, we saw that we get alcohols. And if you think about, if that logic kind of followed with amides, we would also get alcohols and amines. So obviously, uh, we're not getting we're not getting just we're not getting two products. We're getting one product. And so the mechanism is very different in this process, right? Esters, you get two alcohols. With amides, you just get one amine, and the nitrogen it stays on the compound itself. And so in general, the reaction looks like this, where you take an amide, you react it with lithium aluminum hydride. Notice this doesn't even require an aqueous workup, and you generate RCH2NH2. So the carbonyl has been completely reduced to a CH2 group, and that is the only thing that happens. And the question is, well, what's going on here? What is the mechanism? Well, let's take a look at what's possibly happening here. And in general, to be honest, the mechanism is actually not understood very well. With hydrides themselves, the mechanism of hydride reduction with the lithium aluminum hydride and sodium borohydride isn't very well understood. Chemists thought that they understood it for quite some time, and as such, a lot of organic chemistry textbooks explained this reduction as forming these esters. We actually just recently discovered that's not probably what's going on. But we can at least kind of get an idea in our heads about the possibilities of what's happening in this reaction. Because we can compare it to that of esters and see what could be different about the reduction of amides versus the reduction of esters. So in the first step, we do know that a hydride adds, just like it adds to an ester, just like it adds to an acid chloride, and you generate a tetrahedral intermediate. Now, the tetrahedral intermediate you see is that I'm showing you is a little bit different than what I typically show, where the oxygen has a negative charge. It's believed that an aluminum H2, so we've lost another hydride, and that aluminum H2 actually forms a relatively strong bond with the oxygen. So oxygen donates a pair of electrons to the aluminum, and you get this neutral species. Notice there's no charge involved here. And the reasons for this aren't completely understood, but we do know that the nitrogen has a pair of electrons, and what we think happens is that those pair of electrons get donated to the carbon, and you actually lose AlH2O minus. What you generate is this species here, right? So nitrogen now has a double bond to carbon. The hydride, hydrogen has added, which is a poor leaving group, and this is an iminium ion, so it's an imine, a protonated imine. And now that protonated imine can react with another equivalent of aluminum hydride. And so just like carbonyls, hydrides add to carbonyls, they will certainly add to imines. And what you get is now the addition of two hydrides, and you generate an amine. So we're making a primary amine this way. And so this is in a nutshell, what you need to know about the mechanism of the reduction of amides. Amides produce amines in the reduction process. So if we look at an example of this, here we have N,N-dimethyl cyclohexylamide, carboxamide is what it would be called. So N,N-dimethyl cyclohexyl carboxamide reacting with lithium aluminum hydride in ether. 35 degrees Celsius. So notice no water is actually required for this reaction in its workup. And you generate an amine. Um, in essence, what's happening is that carbonyl it gets completely reduced to a CH2 group. And that sums up the reactions of amides.